Okay, so this is a video explaining the factors that affect ionization energy, and there's three, and these three factors then affect one other thing. So the three factors that affect ionization energy are atomic radius. This is basically the size of the atom. The nuclear charge. Now, nuclear charge means the charge of the nucleus, and as neutrons are neutral, that basically means the number of protons in the nucleus. And then something called electron shielding, which I'll get into in a second. So let's look at nuclear charge first. We can see as we go across a period, our nuclear charge is going to increase. It's basically the proton number, right? The proton number is the nuclear charge. And we can see as we go down a group, the nuclear charge also increases by quite a bit, actually. So that's how nuclear charge changes down a group and across a period. We also have atomic radius. Now, if I move that to the side slightly, if we think about the atomic radius across a period, let's look at, for example, lithium and beryllium. So here's lithium and here's beryllium. Well, they're going to have the same number of shells of electrons. Lithium's going to have 2 in its first shell and 1 in its outer. Beryllium's going to have 2 in its first shell and 2 in its outer. However, as lithium only has 3 protons and beryllium has 4, the electrons in beryllium are going to be getting pulled closer in. You can imagine it like fishermen trying to reel in a fish. If this outer electron is a fish, and these here are fishes, here you've got 3 electrons trying to pull in the fish. Whereas here, you've got 4 electrons trying to pull it in, 4 fishermen pulling it in. You're going to be able to pull it in closer, aren't you? And so what actually happens is across a period, because the number of protons increases, the atomic radius decreases. The size of your atom gets smaller. So if lithium was this big, beryllium would be this big, because this extra proton is pulling in the electrons more. Now you might say, well, yes, you've got more protons, but you've got more electrons to pull in. But it doesn't work like that. The fact we've got more electrons here doesn't stop the proton being able to pull it in closer. Okay. We've also got our atomic radius down a group. Now, down a group, if I look at hydrogen, lithium, and sodium, well, hydrogen has just the 1 electron. Lithium has 2 in its first shell and then 1 in the outer. And sodium has 2 in its first shell, then 8, and then 1. So, unlike across a period where the electrons are being added to the same shell, as you go down a group, electrons are being added to a new shell. And that makes a large difference to the atomic radius. You've basically got hydrogen, lithium, sodium. So the atomic radius increases by quite a bit as you go down a group. Finally, we've got this thing called electron shielding. So electron shielding is the number of electrons in an inner shell. So let's look at some examples. Let's say I've got boron and carbon. So here's boron. Boron has 5 electrons, so 2 in the inner shell and then 3 in the outer. And then carbon has 6 electrons, 2 in the inner shell and then 4 in the outer. Now, the number of inner shell electrons, you'll notice, has not changed. The electron shielding here we would approximate as 2 because there's 2 electrons, and here as 2. And in actual fact, and you can stop the tape and figure this out for yourself, as you go across a period, the number of electrons in the inner shell does not change at all. And so the electron shielding will be similar, because you've got the same number of inner shell electrons. Whereas as we go down a group, if I look again at hydrogen, lithium and sodium, I'll get my diagram up from before. In hydrogen, the electron shielding is 0. In lithium, it's 2. In sodium, it's 10. So you're going to have much more electron shielding as you go down a group. Now let's have a think about what effect these have on our ionization energy. Well, as your atomic radius increases, what's going to happen to the ability for your nucleus to hold on to that electron? Now, there's a fancy name for that. We call that the nuclear attraction, the attraction of the nucleus towards the outermost electron. Okay, so this essentially determines our ionization energy. The larger the nuclear attraction, the attraction from the nucleus, towards the outermost electron, the electron being ionized, the larger this is, the more energy it will take to overcome this attraction, and therefore the higher the ionization energy. So whatever happens to the nuclear attraction towards the outermost electron, that is what's going to happen to the ionization energy. This is what determines the ionization energy. So let's have a look at what effect the atomic radius would have on the nuclear attraction towards the outermost electron. Well, if your atomic radius increases, that means your outermost electron will be further away from the nucleus. So have a think about what happens with magnets. As magnets get further away from each other, does their attraction become stronger or weaker? As magnets get further away, it becomes weaker, doesn't it? And the same is true for the attraction between a nucleus and the outermost electron. As they get further away, the attraction becomes lower. And so as your atomic radius increases, the nuclear attraction towards the outermost electron decreases. Let's look at nuclear charge. As your nuclear charge increases, you have more protons in the nucleus, so you have more protons to attract the outermost electron. And so that's going to make the nuclear attraction towards the outermost electron greater. And then we've got electron shielding. Now, electron shielding reduces the nuclear attraction towards the outermost electron. So as we have more electron shielding, the nuclear attraction towards the outermost electron decreases.